Probability that a molecule survives a time t without collision. Focus attention on a particular molecule in a gas at any instant of time. Let W dt be the probability that the molecule suffers a collision during a time interval dt. Consider now the survival probability P of t, which is defined as the probability that the molecule survives a time t without suffering a collision. Clearly, P of 0 is equal to 1. At time t is equal to 0, there is no collision, since it is certain that the molecule survives for a vanishingly short time. It is equally clear that P of t goes to 0 as t goes to infinity, since the molecule must sooner or later suffer a collision. The survival probability P of t must be related to the collision probability omega dt. Indeed, the probability P of t plus dt that the molecule survives a time t plus dt without a collision must be equal to the probability P of t that it survives a time t without a collision multiplied by the probability 1 minus omega dt that it does not suffer a collision in the subsequent time interval between t and t plus dt. By writing down this relation, obtain a differential equation for P of t. Solving this equation and using the fact that P of 0 is 1 show that P of t is e to the minus omega t. So let's write this equation. The probability P that the molecule survives without a collision in the time interval t plus dt is the probability that it survives a time t multiplied by the probability that it doesn't have a collision in the time interval dt, which is 1 minus omega dt, the probability that the molecule suffers a collision in the time interval t. Okay, so using this relation, we find that P of t plus dt minus P of t is equal to, so we take this P of t to the right hand side, minus P of t omega dt minus P of t omega dt. So in the limit that dt goes to 0 for a very short time interval, we obtain P of t plus dt minus P of t divided by dt is equal to minus P of t multiplied with omega. So this is 1 over P. That's the definition of the derivative dp dt. So this is dp dt. And on the right hand side, I'm left with minus omega. Or I can see that minus omega is the derivative of natural logarithm of the probability p with respect to time t. So that is the differential equation I'm looking for P of t. Now, if I solve this differential equation by isolating time and p, so dt goes to the left hand side, I obtain integral from probability p0 to probability p d natural logarithm p is equal to integral from time t0 to t minus omega dt prime. So this gives me natural logarithm of p over p0. Integral of the differential gives us the natural logarithm p minus omega. The integral dt is t, which is evaluated between t and t0, so it is t minus t0. So this tells me that P of t is p0 exponential minus omega t minus t0. Now if I set t0 is equal to 0, I obtain P of t is equal to P0 e to the minus omega t, and I know that for a 0 time interval, the probability P0 is equal to 1. So this gives me P of t must be equal to e to the minus omega t, the answer that I was looking for. The probability of survival for a time t is exponential minus omega, where omega dt is the probability that the molecule suffers a collision. So it is related to the probability that the molecule suffers a collision in the time interval dt. So it's omega dt. So omega times t would be the probability of having a collision in the time interval t, which is, this is the integral of omega dt if omega is not time dependent. Then you would have e to the minus omega t is the probability of the survival. So to summarize, we're focusing on a molecule. We define omega dt, the probability that the molecule suffers a collision in time interval dt, and P of t, the probability that the molecule survives a time t without suffering a collision. And it doesn't suffer a collision at t is equal to 0, so probability of not having a collision at t is equal to 0 is 1, and it should die off as t goes to infinity. And you can see that here, as t goes to infinity, probability goes to 0. It should sooner or later suffer a collision. And this relationship is obtained by noting that the probability of not having a collision from t equals 0 to t equals t plus dt is the probability of not having a collision at time t multiplied by the probability of not having a collision in the time interval dt, which is 1 minus omega dt, the probability of having a collision, omega dt. Okay, so this gives me, by looking at the limit as dt goes to 0, the derivative of probability p with respect to time as minus pt omega. So omega is d ln p dt. That's a differential equation between probability p and probability omega dt. So solving this equation, we find that P of t is P0 e to the minus omega t minus T0. When T0 is 0, we start our timer at t is equal to 0. We have P0 e to the minus omega t. And for a 0 waiting time, P0, we obtain P0 is equal to 1. And therefore, our answer is e to the minus omega t, and it does show this property, that it goes to 0 as t goes to infinity as expected.